You know, I want you to imagine taking off a pair of glasses that you've worn your entire life.
Like a pair you don't even realize you're wearing anymore.
Exactly. You've navigated the whole world with them.
Ah,
You've built your understanding of literally everything around you based on what you see through those specific lenses.
right.
And as far as you're concerned, you are seeing reality perfectly. But then somebody walks up and just hands you a completely different pair.
And suddenly everything looks wrong. Or, well, maybe right for the first time.
Yeah, the moment you put them on, you realize your old lenses were actually like slightly distorted this whole time. The
Ugh.
shapes of the world change.
Wow,
The
yeah.
way light hits your eye changes. I mean, everything you thought was a fundamental, unshakable truth of how the universe looks, it just shifts.
It's a huge paradigm shift.
It really is. So today, we are trying out a completely new prescription for the cosmos. We're asking this massive question. What if everything you thought you knew about how light travels through space was, well, built on the wrong geometric foundation?
It's a staggering proposition to consider, honestly.
Right, because it's the bedrock of modern astronomy.
Exactly. Our focus today is a highly technical, really revolutionary paper by George James Dukas. It's titled Light Signaling Across the Universe.
And he proposes something pretty wild in it, doesn't he?
And he does. He proposes something he calls the TDUFT Phi-Psi Attenuation Framework.
Okay, TDUFT, what does that actually stand for?
It stands for Transdimensional Unified Field Theory. And to understand why this is such a seismic shift, we really have to recognize the comfortable assumptions we've built into standard physics.
Like the stuff we just take for granted every day.
Right. For over a century, we've operated on the belief that the speed of light is a strict constant.
Sure.
We've built our cosmological models on this premise, that the universe is physically expanding, stretching light waves along with the fabric of space.
The classic expanding balloon idea.
Precisely.
Yeah.
And crucially, we've built all our mathematics for light propagation on spherical geometry, utilizing the number pi.
Right, 3.14159, all that.
Yeah, but the framework Dukas proposes, it systematically dismantles that standard model.
Mm.
It just replaces it with a completely new set of dimensional phi-based rules.
Okay, let's slow down for a second, because you just listed off concepts that most people, I mean, myself absolutely included, consider unshakable laws of nature.
They are the pillars of the standard model, yeah.
We are talking about rewriting the entire rule book of reality here.
Basically, yes.
So our mission today for this deep dive is to figure out exactly how this TDUFT model supposedly works, like why it tries to throw out the standard physics playbook, and what it actually means for you and me when we look up at the night sky.
That's a lot to unpack.
It's a ton. And as I was reading through this paper, the sheer scale of the departure from standard physics really hit me. I mean, the author doesn't just tweak Einstein or Hubble.
No, not at all.
They completely replace the underlying mechanisms of how we perceive the universe.
The departure is entirely structural, which is, I think, why it feels so jarring.
Yeah, jarring is a good word for it.
In standard physics, right, when you picture a star emitting light, you intuitively picture a perfect expanding sphere of radiation moving outward.
Like a ripple in a pond, but 3D.
Exactly. And the mathematics of standard physics uses pi to calculate that spherical expansion.
Because pi is circles and spheres.
Right. But the TDUFT model argues that the fundamental shape of reality at the quantum and cosmic scale, it's not spherical.
Okay, so what is it then?
It is tetrahedral, and it's governed by phi, the golden ratio.
Wait, tetrahedral.
Yes, we are moving from smooth circles to structured, multifaceted geometric shapes.
I just want to make sure I'm visualizing this correctly. When you say tetrahedral, we're talking about a pyramid shape, right? Like a base with 3 sides coming up to a point.
That's the basic shape, yes.
It's angular, it has corners. You're saying this theory models the universe not as a smooth balloon of expanding light, but as like some sort of jagged geometric structure.
Well, a multifaceted geometric cascade is a better way to think of it.
A geometric cascade.
Okay. It's not that the universe is full of giant floating pyramids.
Right. That'd be weird.
Very. Rather, the dimensional lattice that space is actually composed of operates on the geometric relationships of interacting tetrahedrons.
Ah, so it's the invisible structure underneath everything.
Exactly. And because of this, the way light fades over distance, what we call attenuation, is fundamentally different.
How so?
Well, standard physics blames a combination of metric expansion, the actual stretching of space, and simple absorption by cosmic dust and gas.
Like light just getting blocked or stretched out.
Right. But TDUFT, on the other hand, attributes the fading of light to what Dukas calls a phi-psi entropy kernel.
A phi-psi entropy kernel. That sounds intense.
It's essentially an inherent decay built into the dimensional structure of space itself. In this model, space isn't stretching at all.
Okay, wait. If space isn't stretching, then literally everything we've been taught about the Big Bang and the expanding universe is fundamentally a misinterpretation.
It would be an optical illusion, basically.
An optical illusion. That is a massive pill to swallow.
Hmm.
And doesn't that inevitably mess with the speed of light, too?
Oh, it absolutely does.
Because everyone knows
Yeah.
the constant, 300,000 kilometers a second in a vacuum. You can't just change that, can you?
You can if you redefine what light is actually doing when it travels.
Okay, I'm listening.
Under TDUFT, light speed isn't a constant number you can just, write on a chalkboard and expect to hold true everywhere unconditionally.
Right.
It becomes a fish-structured operator.
A structured operator, so it changes.
This means the speed of light is a dynamic formula. It depends entirely on the coherence of the specific dimensional environment it's traveling through.
Because it's interacting with that tetrahedral lattice stuff.
Precisely. The light is interacting with that tetrahedral geometry we mentioned. And because it's interacting with a structured geometry rather than just a smooth, empty void, the intensity of light behaves differently too.
Right, the inverse square law.
Exactly.
Like standard high school physics says light spreads out isotropically.
Meaning equally in all directions.
Yeah, getting dimmer the further out it goes as it covers more surface area of that expanding sphere. But if the universe is made of tetrahedral geometry, the light can't spread perfectly evenly, can it?
It cannot. TDUFT posits that intensity is actually governed by a directional inverse square law.
So it favors certain directions.
Yes, it is anisotropic at the fundamental level. It prefers certain alignments based on those tetrahedral structures.
Wow.
And these differences, they culminate in a massive cosmological shift. Think about the FLRW metric.
The FLRW metric. Okay, let's unpack that for a moment for people.
Good idea.
For those who aren't cosmologists, the FLRW metric, that's the Friedman-Lemaitre-Robertson-Walker metric, is basically the mathematical engine of the Big Bang model.
It's the core assumption, yes.
It's the formula that assumes the universe is homogeneous on a large scale and is actively expanding.
Right.
And it's what gives us the concept of a causal horizon, like the idea that if you look far enough out, you eventually hit an absolute edge to the observable universe.
Because the space beyond that point is expanding away from us faster than light can travel toward us.
Exactly.
Well, that is the standard interpretation. But Dukas replaces that entire expanding metric with the concept of a detectability radius.
Detectability radius, so no edge.
TDUFT removes metric expansion entirely from the math of light propagation. So when we look out into the deep cosmos under this new framework, we aren't seeing light fighting a losing battle against a rapidly stretching universe.
Okay.
We are simply seeing the intrinsic natural attenuation of light across a transdimensional structure. The light isn't being outpaced, it just fades away until it structurally falls apart.
It just runs out of juice.
Yes, and the author stitches all of this together by proposing a single unified equation for what he calls the DN fields.
The DN field. Yeah, for my reading, this is perhaps the deepest philosophical shift in the paper.
It's definitely the most foundational.
Dukas proposes this master evolution equation.
Yeah.
And he argues that light propagation, like the actual physical movement of a photon from a distant star to a telescope here on Earth, isn't even the primary event.
No, it's secondary.
It's just a projection. It's a shadow cast by this deeper, shell-indexed mathematical reality happening in higher dimensions that we can't even fully perceive.
Exactly. The observable light we measure is essentially the exhaust or the byproduct of this deeper dimensional equation resolving itself.
That is mind-bending.
It is. And the most crucial element of this entire new theoretical framework, the thing that allows this DN field to actually function, is that it insists on being dimensionless in its core structure.
Dimensionless.
Yes. It is entirely operator-driven, and it completely eliminates pi from the mathematics of cosmic light.
Okay, I have to stop you there. Because the idea of getting rid of pi is the part I find hardest to accept.
It's a huge leap, I know.
Pi is the circle. It is the sphere. Since the days of Archimedes, if you want to calculate anything radiating outward from a central point, you use 3.14159.
You do in standard geometry, yes.
A star is round. It emits light in all directions, creating a larger and larger sphere of radiation. Like, how can anyone possibly calculate the spread of light through space without using spheres and pi? What do you even replace it with?
You replace pi with phi,
Chloe.
the golden ratio, which is approximately 1.618.
But hold on, the golden ratio is about proportions.
It
You
is.
see it in the spiral of a nautilus shell, or the arrangement of seeds in a sunflower, or like classic architecture. How does a ratio of proportions replace a geometric absolute like the circumference of a circle?
Well, in standard physics, when you calculate the surface area of a sphere to figure out how a star's light spreads out and dilutes, the geometric constant you rely on is 4 times pi.
Right.
And that number evaluates to roughly 12.566.
Okay.
This is the absolute cornerstone of the classical luminosity distance equation. But TDUFT demands we throw out 4 pi entirely.
And put what in its place?
A completely new geometric operator called kappa geom.
Kappa.
Yes. And in high coherence limits, meaning local space where the signal is strong and clear, kappa geom evaluates to exactly 12.57.
Wait, 12.566 versus 12.57?
Yes.
Those numbers are frustratingly close.
They are incredibly close.
They're so close that I can immediately see why humanity might have been using the wrong one for centuries without even noticing. If the math is off by less than 1/100th of a decimal point, all our local observations would just seem to confirm the wrong theory.
Precisely. It's close enough to mimic reality on a small scale.
But conceptually, where does 12.57 actually come from if we are using circles? You can't just, pick a number that's conveniently close to 4 pi.
You cannot, and the paper goes to immense lengths to derive this number structurally rather than arbitrarily.
Okay, so break it down.
The constant 12.57 is derived from 2 completely distinct mathematical components. The first is a geometric cascade operator, which gives us the clean integer of 12.
Okay, 12.
And the second is a phi Ramanujan entropy offset, which provides the remaining 0.57.
Got it. Let's start with the 12.
Let's look at the integer 12 first. It comes from the fundamental geometry we discussed earlier, the tetrahedron.
Right, the pyramid shapes. The text specifies that this number 12 comes from 6 distinct tetrahedral cascades.
Let's visualize what a cascade means in this context. In TDUFT, space isn't an empty vacuum. It is a structured lattice.
Like a grid or a jungle gym.
Right. So for a photon to travel, it doesn't just smoothly glide through empty space.
It can't because space isn't empty.
Exactly. It has to propagate by stepping through what the author terms a recursion ladder. It has to successfully negotiate the geometry of the space it occupies.
Like climbing the rungs of a ladder.
Good analogy. The paper identifies 6 distinct geometric steps, or surface closure events, required for light to propagate through this ladder, and each of these 6 steps carries an Euler invariant of 2.
Oh, an Euler invariant.
You're familiar with it.
Yeah, I remember Euler's formula from topology and college geometry. Vertices minus edges plus faces equals 2. It's a foundational truth for any convex polyhedron. Like, if you have a cube, you have 8 vertices minus 12 edges plus 6 faces. That equals 2.
Perfect.
And if you take a tetrahedron, you have 4 vertices minus 6 edges plus 4 faces. That also equals 2. It's like a mathematical seal of approval for a closed 3D shape.
The topological seal is a great way to phrase it. It confirms dimensional closure. Dukas is arguing that light propagation involves navigating 6 of these tetrahedral cascades, each fundamentally defined by that Euler invariant of 2.
Ah, I see the math now.
Right. So you have 6 cascades multiplied by an invariant of 2, which gives you 12.
Boom.
This forms the purely geometric backbone of the operator. Furthermore, the theory states that this Euler invariant of 2 simultaneously acts as the D2-dimensional field clause of photon propagation.
So the topological math and the actual physical dimensional reality are just deeply intertwined.
They are one and the same in this framework.
Okay, that perfectly explains the beautifully clean integer of 12. We have 6 geometric steps, each requiring a mathematical weight of 2. But reality is rarely perfectly clean, which brings us to the fraction.
The messy part.
Yeah. Where does the 0.57 come from? You mentioned a Ramanujan offset, which sounds highly complex.
Well, Srinivasa Ramanujan was a mathematician famous for his infinite series and just incredible intuition with numbers.
A genius.
Yes. The paper utilizes a phi Ramanujan progression to calculate the entropy offset. Because the light is taking 6 structural steps through these tetrahedral cascades, it doesn't do so flawlessly.
It loses something.
It experiences a 6-step loss of coherence. The mathematics describe a sum of phi to the negative Neshan for 6 distinct steps.
Okay, so let me get this straight. As the light moves through step 1, it loses a little coherence based on the golden ratio.
Yes.
And then at step 2, it loses a bit more, but scaled down by the golden ratio again.
Precisely. It is an infinite series mathematically, but it's bounded practically by the 6 physical cascades. When you sum that specific diminishing sequence of phi steps and then multiply it by a finite of entropy constant derived elsewhere in the theory.
The resulting value is exactly 0.57.
Exactly.
Yeah, I'm really trying to picture this in my head. If standard physics is like modeling reality with a perfectly smooth, inflated round balloon,
Okay.
then Dukas is arguing that reality is actually a spectacularly complex, folded origami masterpiece,
I like that.
specifically made of interacting tetrahedrons. But because there's so many tiny folds, it just looks perfectly round from a distance.
Yes.
So the 12.57 isn't an approximation of a circle. It is the exact literal math of the origami folds. We've been using balloon math when we should have been using origami math.
The origami metaphor works quite well, provided we add one crucial physical element to it.
What's that?
The paper doesn't just sit there static. Think about the actual act of folding and unfolding that paper as light attempts to pass through it.
Oh, like movement.
Right. The folds represent the dimensional steps, the physical lattice the light is moving through. And because the universe is not a perfectly smooth balloon, moving through those angular folds, those 6 cascades, requires energy.
There's resistance.
Exactly.
Yeah.
There is friction in the origami lattice. And this brings us to a radical redefinition in the framework, the concept of entropy.
Okay.
If light propagation requires negotiating these complex origami-like cascades, then moving through these dimensional steps exacts a toll.
Right. You can't cross the bridge for free. There has to be a toll booth.
Yes.
But, whenever I hear the word entropy, my mind instantly goes to the second law of thermodynamics. I think of a messy room or like a dropped coffee cup shattering on the floor.
Chaos.
Right. It's the inherent tendency of the universe to move from order toward disorder and chaos. You can't unshatter the coffee cup.
That is statistical disorder, the classical thermodynamic definition.
Right.
But Dukas explicitly demands we discard that definition for this framework.
Completely discard it.
Yes. In Appendix H of the paper, entropy in TDU-FT is explicitly defined not as statistical disorder, but as dimensional resistance.
Dimensional resistance.
It is quite literally a dimensional cost paid whenever abstract geometry descends into observable physics.
A dimensional cost. It's almost like the universe is charging a tax just for the privilege of existing in a physical, observable reality.
It is a tax. And the paper outlines 3 specific tax brackets or entropy operators.
Okay, let's hear them.
There is epsilon, known as the emergence constant. There's epsilon phi, which is the phi progression entropy that generates our 0.57 offset.
Right, we talked about that.
Then there is epsilon prime, which represents time lattice entropy. But the bedrock of this entire concept is that first operator, epsilon, the emergence constant.
I spent a long time staring at the math for this emergence constant because the numbers are so aggressively specific.
They are very precise.
The paper derives the emergence constant epsilon by subtracting one very specific number from another. It takes exactly 3.0000000000 and subtracts 2.9979245 and the result is 0.00207542. We really need to explain what these numbers represent because otherwise it just feels like we're playing with a calculator.
We must ground these numbers in their physical meaning, you're right. The number 3 represents the ideal.
The ideal what?
It is the perfect phi geometric closure value. In a theoretical, frictionless, purely geometric state, the maximum speed of light expressed in units of 10 to the 8th meters per second would be exactly 3.
300 million meters per second on the dot, a perfectly clean integer.
Yes.
But the second number, 2.9979245, anyone who has taken a physics class might recognize that one. That is the actual measured coda speed of light.
Exactly.
CODA being the international committee that determines the accepted values for fundamental physical constants. It's the messy, real-world speed of light that we measure in a vacuum.
Yes. So Dukas is making a profound philosophical and mathematical claim here.
And what's the claim?
He is arguing that the speed of light isn't just an arbitrary universal speed limit that the cosmos settled on randomly. The speed of light is structurally supposed to be exactly 3.
But it's not.
Right. However, a pure theoretical photon, what he calls a massless D8 photon, existing in an 8-dimensional space, it has to descend down into our observable D2-dimensional structure for us to actually detect it.
And that descent comes with a cost.
Yes. To make that descent and physically manifest in our universe, it pays the epsilon toll. It pays the 0.000075542 dimensional resistance fee.
So the real-world speed of light is simply the perfect geometric ideal minus the dimensional tax of existing.
Yes, that is exactly it.
And let's see 2.997 is just the leftover change after the universe takes its cut. Conceptually, I love that. I mean, it's beautiful.
That's very elegant.
But I have to push back hard here.
Please do.
Redefining the speed of light as a perfect 3 minus a dimensional toll fee feels dangerously close to mathematical numerology.
I understand why I'd say that.
I mean, anyone can find two numbers that happen to subtract into a tiny fraction and claim it has cosmic significance. How does this paper prove that this isn't just a mathematical parlor trick?
It is the necessary skepticism of any physicist, and to be fair, Dukas anticipates it.
Okay. How does he answer it?
Well, a model can be mathematically elegant, but if it doesn't accurately describe physical reality, it's useless. To prove this isn't numerology, the theory takes these abstract entropy concepts and builds an entropy attenuation kernel, denoted mathematically as E of R.
E of R, okay.
This kernel is a functional formula that calculates exactly how light degrades as it travels over vast cosmic distances, explicitly using that dimensional toll.
So it puts the math to work.
Exactly. If the theory is valid, this E of R kernel must predict physical phenomena that we can actually observe, test, and verify.
Right. You can't just build an engine on paper. You have to put it in a car and push it to its absolute limits to see if it explodes.
It's a great way to look at it.
You have to apply this kernel to the physical extremes of the universe. And that brings us to what I think is the most mind-bending concept in the entire paper, the blackout radius.
The blackout radius, designated as R black, is really where TDUFT throws down the gauntlet against standard cosmology.
It's a huge claim.
Let's revisit the standard model first. We talk about the edge of the observable universe, the causal cosmological horizon.
Right.
We believe we can't see past a certain distance because the universe has been expanding since the Big Bang, and the space between us and those distant ancient galaxies is stretching faster than their light can physically travel toward us.
The light is essentially trapped on a cosmic treadmill.
Yes. But remember, TDUFT threw out metric expansion entirely. We established that space isn't stretching in this model.
Right, space is static. So if space is static, shouldn't we be able to see infinitely far in every direction? Like, why is the night sky mostly dark?
We can't see infinitely far because of that E of R kernel. The dimensional resistance is cumulative. The blackout radius is defined as the exact calculable distance at which light intensity drops below a pure detectability threshold, entirely due to the geometric spread and that entropy toll.
Wow. So the light isn't being outpaced by expanding space.
No. It is quite literally losing its structural coherence the further it travels through the transdimensional lattice. It pays the toll at every node until it has nothing left.
The paper sets a specific mathematical baseline for this blackout point. It defines a minimum intensity threshold of 10 to the negative 20th power watts per square meter.
Which is incredibly faint.
That number is almost impossibly small. It represents the absolute dimmest whisper of a photon that a perfectly calibrated instrument could theoretically detect before the signal is completely swallowed by quantum noise.
It is the absolute floor of physical detectability, yes.
Right.
The paper provides two distinct examples to demonstrate how this works. It calculates the maximum possible detectability distance by setting that entropy kernel to its high coherence upper bound.
Okay, what's the first example?
The first example applies the formula to our own sun. If you took our sun with its specific luminosity and you slowly backed away from it in this TDUFT universe, at what precise distance would its light completely black out and cease to exist as a detectable signal?
And the formula calculates a blackout radius for the sun of roughly 5.83 million light years.
Yes. And we have to put that scale into context.
Definitely.
The Andromeda Galaxy, which is our nearest major galactic neighbor and the furthest thing you can see with the naked eye under perfect conditions, is about 2.5 million light years away.
Okay.
So if you were standing in Andromeda with a telescope capable of detecting 10 to the negative 20th watts per square meter, you could theoretically still detect our sun.
It's pretty far.
It is. But if you traveled a bit further out, past that 5.83 million light year mark, the sun's light simply ceases to be a coherent signal.
It has paid too much dimensional tax.
Exactly. It vanishes entirely from the observable universe.
Okay, 5.83 million light years for a single relatively average star makes logical sense. But the second example the paper uses is way more extreme, and this is where it directly attacks the current standard model.
It certainly does.
The paper applies the blackout radius formula to MOMZ14.
A very important target.
For our listeners, MOMZ14 is a highly redshifted galaxy recently observed by the James Webb Space Telescope. It is one of the most distant ancient structures humanity has ever found, Looking at it is literally looking back to the dawn of time in standard cosmology.
And this is where the divergence between the models becomes undeniably stark. According to standard NASA and JWST calculations, which rely on the standard lambda CDM expanding universe model, the luminosity distance to MOM Z14 is roughly 13.5 billion light years.
13.5 billion light years. And that aligns perfectly with the standard accepted age of the universe, which is around 13.8 billion years.
It fits the timeline perfectly, yes.
But when Dukas takes the exact same observed radiant power of MOM Z14 and runs it through his phi-based geometry and the EVAR entropy kernel, what is the TDUFT blackout radius?
The TDUFT calculations yield a blackout radius for MOM Z14 of approximately 847 billion light years.
847 billion light years.
Yes.
That is a number so large it breaks the brain. It is massively larger than the standard model's distance and exponentially larger than the accepted age of the universe.
That's a profound difference.
If a galaxy can be visible from 847 billion light years away, then the universe cannot possibly be only 13.8 billion years old.
That is the inescapable implication, and the author is very careful to clarify what this number actually means.
Right.
847 billion light years is a pure detectability threshold. It is not a causal horizon created by time and expansion.
So no edge.
Correct. If this TDUFT model reflects reality, our universe doesn't have an edge shaped by a Big Bang. Structures just exist, and their light travels through the lattice until it fades into the dimensional structure and becomes strictly invisible.
Next time you look up at a pitch-black patch of sky through a telescope, you really have to think about that.
It changes your perspective.
Standard physics tells you there's nothing there because the universe hasn't expanded that far or light hasn't had enough time to reach us since the beginning of everything.
Right.
TBUFT tells you there might be an entire empire of ancient galaxies sitting right there, but their light is just too tired. It paid too much dimensional tax traversing the origami folds of space, and it fell apart just before reaching your lens.
It's a haunting image.
It's the difference between a car driving off the physical edge of a map versus a car just running out of fuel on an endless, eternal highway.
The mechanical limitation versus the structural limitation. But as captivating as that eternal highway is, a cosmological model cannot survive on billion light-year predictions alone.
Yeah, that's true.
It is easy to make grand claims about the edge of the universe because they are incredibly difficult to disprove. A theory must be able to predict the mundane just as accurately as the profound.
Exactly. If I invent a brand new type of tape measure, you don't test it by asking me to measure the distance to the moon.
Oh, no, you do not.
You test it by asking me to measure the length of your living room. If TDUFT is going to completely upend astronomy, it has to accurately predict the universe right in our own backyard. And chapters 8 and 9 of the paper tackle this local testing head-on. Dukas actually calls this the strongest empirical result of his entire framework.
TDUFT has to prove it can calculate local distances without breaking the physics we already know works.
Right.
The ultimate reality check for this is the distance between the Earth and the Sun, the foundational yardstick of astronomy, known as 1 astronomical unit, or 1 AU.
Historically, determining 1 AU was one of the greatest challenges in early astronomy. We've refined it over centuries using radar and telemetry, and standard physics dictates that 1 AU is exactly 149,597,870,700 meters.
Very precise.
Let's just call it 1.496 times 10 to the 11th meters. It's a rock-solid, indisputable number. So if we throw out pi and use this new phi-based math, how does TDUFT attempt to calculate our distance to the sun?
It requires an empirical calibration of the TDUFT luminosity equation. But because we are dealing with our own solar system, the conditions are unique compared to deep space.
Because we're so close.
Yes, we are incredibly close to the source of the light. We are operating in what the paper defines as a high-coherence quasi-isotropic limit.
Let's break that phrase down. High coherence means the light hasn't traveled far enough to pay a significant dimensional tax yet, right?
Correct. Because the distance is relatively minuscule on a cosmic scale, the entropy kernel, EVAR, functionally approaches 1.
It hasn't degraded.
Exactly. Furthermore, the directional beaming of the star, represented by the operator G theta, also approaches 1.
Meaning locally, the sun's light appears to be spreading perfectly evenly in all directions.
Yes. And crucially, because we are in this high coherence local limit, our new phi-based geometric operator, kappa geom, evaluates fully and perfectly to 12.57.
Okay, so using my earlier analogy, we're standing so close to the origami folded paper that we can't even see the creases.
Right, it looks perfectly smooth to us.
The framework elegantly collapses down into something that just mimics standard classical physics.
It mathematically simulates the classical sphere locally. The paper details an inversion formula to prove this.
How does it work?
The author takes the known, definitively observed radiant power of the sun, its absolute luminosity. He takes the measured solar flux hitting the Earth, which is literally the physical amount of sunlight striking a square meter of the Earth's atmosphere.
Hard data.
Yes. He plugs those two strictly observed numbers into the TVU-FT distance equation, but he uses the 12.57 origami constant instead of the standard 4 pi geometric constant.
And what does the math spit out?
It flawlessly recovers the exact Earth-Sun distance, 1.496 times 10 to the 11th meters.
Wow, okay. The tape measure works in the living room. It produces the exact same number.
It does. And from a theoretical standpoint, this is a monumental achievement.
It really is.
It proves that this highly radical, transdimensional, tetrahedral geometry gracefully collapses into standard classical results when you are observing a local, highly coherent, spherical-looking star. It doesn't break classical physics, it encapsulates it and expands upon it.
I see why the author is proud of that, but honestly, this raises a massive red flag for me.
Oh, why is that?
If TDUFT gives the exact same numerical answer for the Earth-Sun distance as standard physics does, how do we know which underlying theory is actually true?
That's a fair question.
I mean, if the math spits out 1AU either way, aren't we just choosing between two different philosophical flavors of the exact same physical soup? One is pie-flavored, one is phi-flavored, but the outcome is identical. How is this practically useful?
Your red flag is entirely justified. If a new theory only ever reproduces the exact same results as the old theory, it is mathematically redundant.
Right.
The utility of TDUFT and the way to prove it is fundamentally superior to standard physics lies in the accuracy regimes discussed in the paper's appendices.
Okay, tell me about those.
The model works perfectly in tandem with standard physics for the sun because the sun is stable, nearby, and highly coherent. The author acknowledges that TDUFT will match classical physics almost perfectly for any nearby main sequence stars, red giants with stable atmospheres, or standard white dwarfs.
So for the well-behaved local neighborhood stars, both theories work fine.
Yes. But the divergence, where the two theories will produce wildly different predictions, occurs in the degraded accuracy regimes.
The extremes.
Standard physics begins to struggle when observing stars with strong directional beaming, rapid rotators, or stars deeply obscured by heavy cosmic dust and extinction.
It starts getting messy.
Standard physics has to constantly correct for these anomalies with ad hoc reddening laws and manual beaming corrections patched into the equations. TDUFT claims to handle all of these anomalies inherently through its G-theta beaming operator and its E of R coherence kernel.
So the corrections are built into the fundamental DNA of the math, not slapped on as an afterthought. That's a bold claim. But again, how do we physically prove it? We can't just take the author's word that his math handles dust better than Hubble's math.
We look to external validation. The paper explicitly calls for testing the framework against independent geometric anchors.
Independent anchors, meaning
We have to move beyond our solar system but stay close enough to verify the math. The primary method for this is comparing TDUFT distances against Gaia mission parallaxes.
right, the Gaia Space Observatory. It's mapping billions of stars in the Milky Way using parallax.
Yes.
Which is basically measuring how a star seems to shift against background stars as the Earth moves around the sun. It's pure geometry, no luminosity assumptions required.
Exactly, pure geometry. We also need to test it against eclipsing binaries.
What are those?
These are binary star systems where the orbit plane is perfectly aligned with Earth, so the stars pass in front of each other, periodically blocking each other's light.
Oh, I see.
By measuring the timing of those eclipses and the light curves, we can calculate their distance with incredible precision, independent of expanding universe metrics.
Okay, that makes sense.
And finally, maser distances.
Masers. Microwave lasers naturally occurring in space, usually around dying stars or massive black hole.
Yes. The water masers in the accretion disks of certain galaxies give us incredibly precise geometric distances based on their orbital mechanics.
Nice.
So the ultimate test for TDUFT is this. We must take thousands of stars and galaxies. We calculate their distance using the standard pi-based physics. We calculate their distance using the TDUFT phi-based physics,
And then compare them.
and then we compare both of those results to the hard geometric realities provided by Gaia, eclipsing binaries, and masers. The theory that produces the smaller systematic error across massive data sets is the true geometry of the universe.
We have to find the tiny microscopic deviations in deep space where standard pi math gets it slightly wrong and the phi origami math gets it exactly right.
Yes.
The Earth-Sun test proves the model is empirically anchored. The Gaia tests will prove if it truly represents a revolution in physics.
That's the hope.
But assuming it passes those tests, assuming this transdimensional lattice is real, we have successfully avoided the biggest, most glaring elephant in the room of standard astrophysics.
Ah, yes.
If you are an astronomy buff, you've probably been screaming this at your device for the last 40 minutes. If space isn't expanding, what on earth is happening with redshift?
Redshift is the cornerstone of modern cosmology. It is the absolute primary evidence we have that the universe is expanding.
Exactly.
If you remove the expanding metric, you must provide a bulletproof alternative explanation for redshift, or your entire framework collapses.
For the listener, let's establish clearly what redshift is in the standard model.
Sure.
When we observe a distant galaxy, the light we receive from it is shifted toward the red end of the electromagnetic spectrum.
Because the waves are longer.
The standard explanation is metric expansion. The space between us and that distant galaxy is physically stretching. As the photon travels through that stretching space, the wave itself gets stretched out.
Yes.
It's like drawing a squiggly wave on a rubber band and then pulling your hands apart. The wave gets longer. In physics, a longer wavelength means redder light.
The rubber band analogy is the quintessential illustration of metric expansion. But TDUFT rejects the rubber band entirely.
No stretching at all.
There is no stretching fabric of space. Instead, the paper defines redshift as a lattice wave alignment change.
A lattice wave alignment change. That sounds incredibly dense. Walk me through the actual physical mechanics of what that means for a photon.
We have to return to the core concept. Space is a structured transdimensional lattice.
The origami.
Light is a wave propagating through the specific nodes of this lattice. The paper provides an equation for redshift, which states that 1 plus ZZ being the redshift value equals F of phi E PSIE divided by F of phi D PSD.
I'm going to need you to unpack those variables. F, phi, PSI, E, and D.
Certainly. F represents the stabilized local frequency of the light at any given node in the lattice.
Okay, frequency.
Phi is the wave geometry operator we've discussed, how the wave interacts with the tetrahedrons. Psi is the time density or alignment operator, how the wave synchronizes with the dimensional structure.
Got it. And the E and D?
The subscript E stands for emission, the exact moment and state the light was in when it left the distant star. The subscript D stands for detection, the state of the light when it finally hits the mirror of a telescope on Earth.
Okay, so the redshift formula is just a complex ratio comparing the frequency state at the starting line to the frequency state at the finish line.
Basically, yeah.
That makes sense.
Mhm.
But if the space between the start and finish lines isn't stretching, what actually causes the frequency to change so drastically?
The mechanism is what Dukas calls path-integrated attenuation.
Path-integrated attenuation.
As the light travels through the dimensional lattice, moving across vast cosmic distances from node to node, it inherently undergoes a cumulative rebalancing.
Because it's hitting those nodes.
Yes. The physical interaction with the rigid lattice structure itself forces a shift in the alignment of the wave. The wave has to constantly renegotiate its geometry to keep moving forward.
Wow.
That constant renegotiation, that shift in alignment, is what we visually observe as cosmological redshift.
Okay, let me try a new analogy to see if I grasp this.
Go for it.
If standard physics redshift is like drawing a wave on a rubber band and pulling it apart, TDUFT redshift is more like a cosmic game of telephone.
Telephone.
Yeah, the game. The message, the beam of light has passed through billions and billions of dimensional nodes, which are the people in the telephone circle.
I see.
As the message is whispered from person to person over massive distances, the pitch of the voice naturally deepens with every single transfer.
Ah.
It's not because the people in the circle are physically running away from each other. It's because the act of passing the message through the medium inherently alters the signal due to the friction of the transfer.
The cosmic telephone idea captures the degradation beautifully, but we need to emphasize the structural element to make it entirely accurate.
The structure of the lattice itself.
Yes, the wire itself, the lattice, is what's actively forcing the pitch to change. It's a rebalancing act. And here is perhaps the most meticulous and disruptive point the author makes regarding this process.
What's that?
In the TDUFT framework, redshift and luminosity distance are mathematically independent,
Wait, independent.
completely independent.
That fundamentally breaks modern observational astronomy. In the standard model, redshift literally is distance.
Yes, it is.
The redder a galaxy appears, the faster it is moving away from us due to expansion, which means the further away it must be. They are inextricably linked. Hubble's law is built on that premise.
Standard cosmology firmly locks the two together, yes, but TDUFT cleaves them apart.
Just separates them entirely.
In this model, redshift is an alignment change strictly dictated by the lattice interaction. Distance is an attenuation decay strictly dictated by the entropy kernel.
Okay, I follow.
The text explicitly states that a high redshift value does not automatically modify or guarantee a vast distance unless you explicitly insert an attenuation functional into the math. They are compatible phenomena. They both occur simultaneously as light travels, but one does not intrinsically dictate the other.
That is a staggering paradigm shift. It means you could theoretically observe a galaxy that is incredibly redshifted, but its actual physical distance, calculated purely geometrically, might be radically different than what standard expansion models predict.
Exactly. It decouples the two foundational pillars of modern astrophysics.
And reading further into the appendix, the paper claims this single structural explanation, the lattice alignment change, accounts for all known types of redshift, doesn't it?
It does, which is a testament to its unified ambition. Standard physics has distinct explanations for different redshifts.
Right, like Doppler redshift is caused by physical motion through space, like a police siren changing pitch as it drives past you.
Yes, and gravitational redshift is caused by light fighting to escape the massive gravity well of a dense object like a black hole.
And then cosmological redshift is caused by the metric expansion of space.
But Dukas argues that under TDUFT, Doppler, gravitational, and cosmological redshift are all manifestations of the exact same phenomenon. The Fibsy operator pairs rebalancing the light wave's alignment within the transdimensional lattice.
It all comes back to the origami lattice. It's a completely unified view of phenomena we previously thought required entirely different mechanical explanations.
It's elegant in that way.
We've covered an incredible amount of ground today, and honestly, it requires a complete mental reset to visualize the universe this way.
It's exhausting, but fascinating.
We started by throwing out pi and the smooth, expanding spherical balloon of standard physics, replacing it with the rigid, interacting origami tetrahedrons of the Golden ratio and the 12.57 geometric constant.
We had to completely redefine entropy, moving away from the classical idea of a messy room and statistical disorder, and toward a dimensional toll fee.
A resistance that explains why the real-world speed of light is just a tiny fraction less than a perfect geometric ideal of 3.
Yes. We explored how that dimensional exhaustion creates a mathematical blackout radius where light doesn't just get outpaced by expansion, but physically runs out of geometric coherence and vanishes.
We saw how this phi-based math perfectly recovers the 1 AU distance to our own sun, proving it can operate in reality, and we explored how it completely reimagines redshift as a structural interaction with the medium of space rather than a stretching rubber band.
It is an overwhelming amount of information to process. It fundamentally demands that you let go of the visual metaphors and foundational assumptions you've been taught since you first looked at a science textbook.
It really does.
But it replaces them with a framework that, mathematically at least, appears remarkably elegant and internally consistent. And this highlights why critical thinking in theoretical science is absolutely vital. We must view alternative models like TDUFT not merely as abstract contrarian curiosities, but as necessary pressure tests for our standard assumptions about the cosmos. Standard physics has incredible predictive power, but we must acknowledge that it currently relies heavily on dark matter, dark energy, and an expanding metric that we cannot directly observe or fully explain.
That's a great point.
Frameworks like the one Dukas proposes force us to confront a difficult question. Are we inventing invisible forces and ad hoc corrections just to make our pi-based spherical math work, or have we simply been using the wrong geometric foundation from the very beginning?
That is the perfect question to end on, and it leaves me with one final thought I want you to mull over. If George James Dukas is right, and the limit of our observable universe isn't a hard physical edge caused by the timeline of an expanding bubble, but is purely a blackout radius, a strict detectability threshold, where light simply runs out of geometric coherence and fades into the dimensional lattice. then the darkness between the stars isn't actually empty space.
No, it wouldn't be.
It's an ocean of signals that are just barely too faint, two-dimensionally exhausted for our current instruments to perceive. Think about that next time you look at the night sky. What ancient, impossibly massive structures are sitting out there in the dark, existing just outside our 10 to the negative 20th power threshold, simply waiting for us to figure out how to build a better dimensional receiver.
A powerful thought.
The universe isn't a balloon expanding into nothingness. It's an origami masterpiece that just gets too dark to read. Keep questioning the universe, everyone. Put on those new glasses and see what changes. We'll catch you on the next deep dive.